Welcome back. Let's continue using substitution to find a few more indefinite integrals. So here I've got the integral of sine cubed times cosine. And so right away I'm thinking about the fact that the derivative of sine is cosine. So I'm saying to myself that I should let u be sine of t. And so du, the derivative of u is cosine t dt. So the sine cubed t, since sine of t is u, then sine cubed is u cubed. And cos t dt, well, that's just du. So this one's a nice quick one to do. U to the 4 over 4 plus c, which is sine to the 4 of t over 4 plus c. Now, this is where things can get a little bit more complicated. So if you're looking and comparing this with the last one, again, we've got cosines and sines, and we know the derivative of sine is cosine. We know the derivative of cosine is negative sine, but either of those substitutions will sort of fail you here, because here, let's suppose I were to let u be cosine of theta. And then du would be negative sine theta d theta. And maybe I would do the same thing and say, well, I'll change that to negative du is sine theta d theta. I would be able to now say for my integration that instead of cos cubed, it would be u cubed. I have sine squared theta d theta. Sine theta d theta would be du, but then I'd have another sine theta left behind. And unfortunately, what would I do with that? Unfortunately, it's not the same thing as u, and it's certainly not du, because I've already replaced one of the sine thetas with d thetas with du. And now I have something where I'm integrating with respect to u, but I still have this other variable mixed inside. If you're remembering what I said before, when we do our substitutions, things need to be completely replaced. So all of one variable has been replaced with the other. So as it currently stands, my substitution is not going to work for me, and so that means I might have to do something to the integrand to get it into a position where I can actually do what I need to do. So again, I'm going to use the fact that the derivative of sine is cosine, or you could use the derivative of cosine as negative sine, whichever you prefer. But I'm going to have to do a little bit of a rewrite here so that instead of having a sine squared or a cosine cubed, that I either have a single sine of theta or a single cosine of theta left behind. So my plan here, what I'm going to do is I'm going to get a single cosine left behind, and I'm going to do it in the following way. Cosine cubed is really cosine times cosine squared. And I know that cosine squared could be rephrased as 1 minus sine squared. And now I'm in a position to start doing the substitution, because if I were to let u be sine of theta, then du would be cosine of theta d theta. And I have a bunch of sine thetas and one single cosine theta left over. So when I do this substitution, 1 minus sine squared would be a 1 minus u squared. Sine squared would be a u squared. And the cosine d theta, that is du. So I did manage to substitute everybody from thetas into u's. So now I have an integral just in terms of u, and I'm just going to expand that. That's u squared minus u to the 4. And when I integrate, I'll get u cubed over 3 minus u to the 5 over 5 plus our constant c. And now I can go back and substitute in what u was, which was sine of theta. So sine cubed theta over 3 minus sine to the 5 theta over 5 plus our constant c. And so that's sort of something that we're going to need to be aware of in the future, that when it comes to doing substitutions, it might not always be obvious, and we might have to do some work to get it into a position where we can do a substitution. Here's another example of that. If I'm looking at these, I see I've got tangent to the 6 and tangent to the 4. And right now I'm in all sorts of trouble because I don't know what the antiderivative of tangent is. I also know that I am having trouble doing any sort of a substitution, because the only thing maybe that I might let u be might be tangent of some sort, but the derivative of tangent is secant squared, and I don't have a secant squared appearing here. So I need to think about what can I do to change this. And I'm noticing to myself, well, if I did take those tangents and factored a tangent to the 4th out, then I'd be left with tangent squared plus 1. And that's reminding me of a lovely Pythagorean identity. Tangent squared plus 1 is secant squared. So actually, I could rephrase this. So instead of tangent to the 6 plus tangent to the 4, it's tangent to the 4 times secant squared. And now I have something where I can do a substitution. If u were to be replacing tangent, then du would be the derivative of tangent, which is secant squared times d theta. And so now I have something to replace secant squared d theta. That'll be my du. I have something to replace the tangents. Those are u's. So now what I'll have is tangent to the power of 4, or u to the power of 4, and secant squared theta d theta, that is du. So I'm just integrating u to the 4, and that's going to give me u to the 5 over 5 plus our constant c. And then last thing for me to do, of course, is go backwards and put in what my substitution was. So since u is tangent, then we'd have tangent to the 5 over 5 plus c. Okay, one other last one. This one sort of seems like a funny one, and this one doesn't seem like an obvious choice for you to do a substitution. And the reason why it doesn't seem obvious is you can say to yourself, well, who would you choose for u, and then how would du pop up into this? So for example, if you're letting u be x minus 1, x is not the derivative, and if u was x minus 1 is not the derivative. Same thing, the square root is also not the derivative. I'm having trouble finding something where I also see its derivative. But here's a sort of a nice little thing to think about here. If I had this slightly different, if this integral wasn't x times root of x minus 1, if it was some sort of polynomial times a root of x by itself, if I didn't have the x minus 1, that would be actually not too bad for me to deal with, because I would be able to multiply that root against all the terms and then maybe expand things and maybe integrate from there. So that's kind of my idea here, that I'm thinking to myself, what if instead of square root of x minus 1, what if it was just square root of u? So what if u was replacing my x minus 1? I mean, in that case, du would be the same thing as dx, so I could go ahead and replace that. So I would have integral of, instead of square root of x minus 1, it would be square root of u. And instead of dx, it would be du. But then the question is, well, what do I do with the x that's in front? And so here's the other part. If u is the same thing as x minus 1, then that's the same thing as saying that x is the same thing as u plus 1. So actually, I could say instead of x times root of x minus 1, I could say we have u plus 1 times the root of u. And then that makes things a little bit nicer for me, because like I said, now that this is no longer root of x minus 1, but just root of a single variable, I could multiply that against the u and against the 1. I'd have u times u to the half, which is u to the 3 halves. I'd have 1 times root of u, which is u to the 1 half. And now I'm finding the integral of that with respect to u, and that's easy enough to do. I'm just going to add 1 to the power, divide by the power, add 1 to the power, divide by the power, and plus constant c. And then last thing for me to do is just to clean this up. So divided by 5 halves is 2/5. And instead of u to the 5 halves, I'll have x minus 1 to the 5 halves. And I'll do the same thing with the next term. Flip that 2/3. And u to the 3 halves becomes x minus 1 to the 3 halves. And there we go, we found our antiderivative. This clever little technique, that can also work in a place where maybe you have something where in the denominator has x minus 1, and it would be a lot nicer if the denominator was an x instead. So if you had some terrible polynomial with an x minus 1 in the denominator, maybe a little substitution there could help you out. So this is one of the places where we have other little clever ways in which substitution can help apart from the obvious ones. Okay, so let's solve this little differential equation, and then we'll have ourselves a pause. I have a differential equation, and I have an initial condition, and I know that if I'm solving a differential equation and it's written as dy dx equals a bunch of stuff with just x's, then to solve, I would need to integrate my derivative with respect to x. And then after I do this, I'm going to get some function of x involving a constant. Afterwards, I'll use my initial condition to find out what that constant c needs to be. So I'm taking a look at this. I've got this polynomial times cosine of this polynomial. And I know if I look at this 8x cubed plus 12x, its derivative is 24x squared plus 12, which doesn't match what I've got left behind. If I look at the x to the 4 plus 3x squared and I take its derivative, I get 4x cubed plus 6x, which is close to what I've got here. So I'm just going to do a little bit of work on the side here. I'm going to say that if we were to let u be x to the 4 plus 3x squared, then we know that du would be 4x cubed plus 6x dx. Like I said, that's not exactly what I have, but I can make it what I have by if I multiplied by 2. 4x cubed plus 6x, if I multiply that by 2, that'll give me the 8x cubed plus 12x. So it looks like 2 du should be 8x cubed plus 12x dx. So I guess now we're ready to do our substitution. Cosine of x cubed plus 3x squared, it becomes cosine of u. And 8x cubed plus 12x dx becomes 2 du. So actually that's a much nicer integral to look at. So integrating 2 cosine u du, and that should be 2 sine u plus constant c. Of course, I need to go backwards and substitute in and say what u is. So I'm going to go and replace the u with x to the 4 plus 3x squared. And now I'm going to use my initial condition. We are told that y of 0 equals 5. So we'll have 5 as our y value when I put in 0 for x. When I put in 0 for x, 0 to the 4 plus 3 times 0 squared is 0. Sine of 0 is 0, 2 times 0 is 0, so I'd have 5 equals 0 plus c, or just 5 equals c. And so now that I've solved my initial condition, I can say that my solution for that differential equation is 2 times sine x to the 4 plus 3x squared plus 5.